So it's my pleasure to continue the morning session by introducing Reynold Fregoli from the
University of Zurich.
The University of Zurich.
Great. Thank you so much, and thank you, big thank you to the organizers for the invitation. So this lecture is meant to be very elementary in a sense, and it's an introduction to the Dani correspondence, which is some sort of dictionary between Diophantine approximation, so number theory, and homogeneous dynamics. So I will take it slowly and give you a very simple example of how the correspondence works and one simple application of this. And of course it has many, many more applications that I won't be able to show you. Okay, so as I said, I also want to say a couple of words about how these lectures are organized. So, okay, in lecture 1 I will give you some motivation. So, in particular, I will introduce some questions in Diophantine approximation that I want to address, and I will give you some properties. I will start giving you some properties of the spaces where the dynamics will take place. Then, in the next lecture, I will define properly all the spaces where I want to do dynamics. And in the third lecture, I will really explain to you or prove the correspondence and give applications. Okay, so let's start from motivation. So the goal of Diophantine approximation, which is our main application in number theory, is to approximate real numbers alpha with rational numbers. So we know that rational numbers are dense in the real line. So you can always find a sequence that converges to alpha. But a more interesting question is the following. Suppose I give you some positive integer as a bound. So bound for the denominator q. How close can p over q be to alpha? And this, of course, depends on the choice. Well, it's not clear, but in principle, it should depend on the number alpha. And the basic result that, well, probably everyone knows and that you've certainly seen is Dirichlet's theorem, which is where I want to start from. So, theorem. I don't remember the date exactly. It's somewhere in the 19th century. So, 19th century. Anyone knows? I'm not sure.
1840.
1840. Okay, great. So, around 1840. Okay? And so it says the following. So for all real numbers alpha and all bounds q greater than 1 on the denominator, there is a rational p over q such that the following holds. So alpha minus p over q is less than 1 over small q times big Q, and small q is less than big Q. Okay, so you can always come this close to your rational number. And the proof is essentially a triviality. Okay, so it's the pigeonhole principle. So you can always assume to work in 0, 1. So subdivide 0, 1 in intervals of length 1 over big Q, where your big Q is fixed, and consider the sequence 0, alpha, 2 alpha, up to big Q alpha. So then these are big Q plus 1 numbers. Okay, here you have your interval. Oh, sorry, I forgot to say that you consider the sequence modulo 1. Okay, so essentially you see the sequence on the unit circle. You subtract the nearest integer to each of these numbers. So when you consider this sequence, you always get elements in this interval 0, 1, which you have subdivided into several intervals. And since you have q plus 1 numbers and q intervals, there will be one interval where you have 2 numbers. And so this implies that there are q1, q2 less than q, q1 different from q2, such that q1 alpha minus some integer p1 minus q2 alpha minus some integer p2 is less than 1 over big Q. Okay, and from this you just conclude. You have alpha minus p1 minus p2 divided by q1 minus q2 less than 1 over big Q, q1 minus q2. And clearly q1 minus q2 is less than q. Okay, so the proof is really easy. But I want to use this theorem to give a motivation to the following definition. So once I know that for every number alpha I can do this, and there's a very easy proof, my first question is, can I improve this theorem? Okay, so I give the following definition. So alpha in R is epsilon Dirichlet improvable where epsilon is some number between 0 and 1 if for all q sufficiently large, the system so alpha minus p over q less than epsilon divided by q, small q, big Q, and q less than q has a solution. Okay, so it's essentially a stronger version of this, where you replace the constant 1 by epsilon. Okay, and the question is, I will denote the set by di epsilon. So the question is, what is the size of di epsilon? Or I will also introduce another set, which I called the set of singular numbers. So this is the intersection for all epsilon between 0 and 1 of the sets di epsilon. So the numbers alpha, for which I can do this for all epsilons between 0 and 1. So another question is also, what about the size of singular vectors? Singular numbers. Okay, so numbers for which perhaps, so I can do better than any epsilon here, so maybe I can also replace this with some kind of function. Okay. And finally, another question in Diophantine approximation that I'm interested in comes from a corollary to this result. So an immediate consequence of Dirichlet's theorem is the following. So since you know that this holds, you also know that for all alpha in R, there are infinitely many values of q for which alpha minus p over q less than 1 over q squared has a solution. Or let's say a solution P. Okay? So this is clear because you know that small q is less than big Q, so you can just replace big Q by small q. Maybe I shut the door. Okay, this is all nice and easy. And so this corollary gives me so the opportunity to introduce also another category of numbers, which is all those numbers for which I cannot improve this. So here I have 1 over q squared. Perhaps you might ask about numbers where I can replace 1 over q squared by some other function of q. So 1 over q cubed, right? And I want to know if this is possible. So I give the following definition. So alpha in R is badly approximable if for all q larger than small q larger than 1 I have, so it holds alpha minus p over q larger than some constant c alpha divided by q squared, where c alpha only depends on alpha and is some positive fixed constant. So why do I introduce this category? Well, these are the numbers for which this function here cannot be improved, maybe only by a constant. Okay? So this is the reason why these numbers are interesting to study, and actually we know a lot about these two sets. Okay, so we know about the set of singular numbers, we know how big it is, and we know about more or less we know about epsilon Dirichlet provable numbers, and we also know the size of this set. When I say size, I mean the measure. Okay, so we know that, for example, this set here has Lebesgue measure 0, but full Hausdorff dimension. Okay, and this set here also has Lebesgue measure 0, but full Hausdorff dimension. Okay, but okay, and the techniques that people have been using to address these problems until probably 40 years ago are based on continued fractions. Okay, so remark, one can say.
Dimension 1 is singular, maybe empty.
Sorry?
In dimension 1 is singular, maybe empty.
No, it's badly approximable and rationals. It's a very strange thing. So the singular points are badly approximables.
That's an intersection?
It's an intersection, yeah.
Okay.
It's it's very strange. I agree with you, but it's so somehow these are the numbers for which you can. So definitely for rational numbers you can do this. Okay.
I agree.
You agree. Okay. So and there's a strange reason for which you can also do it for do that for.
What if I put in C alpha over 2 as my epsilon?
Your epsilon here.
Yeah, C alpha over 2. I have an alpha that's badly approximable. I think I'm just missing something. So I think the inequalities are not the other ways.
C alpha over 2.
Because big Q is smaller than Q squared. Sorry.
C alpha over 2. No, it's a good question.
So probably well approximated rationals.
Sorry? Say again?
So singular, so in equation says that they must be well approximated or rational.
Right.
Am I right?
Then they are half of Leibniz zero, full half
Let's see. Okay, no, it's a really good question. Okay, so you're saying if I put here C alpha divided by 2, and here Q squared. Okay, but let's see. Okay, so definitely these numbers are bigger. Q squared for OQ. Yeah, that's a good question. I don't remember actually. I think this is still true. But probably I'll not to interrupt the flow of the lecture. I'll get back to you later. Okay. But anyway, this is definitely not empty. At least rational numbers are here. Okay. And it should be true. It should be true that thing is rationals union badly approximated. But okay, for now let's put a question mark there. Okay. So I was saying that one can use continued fractions to solve these problems. Okay, but what we want to do is to actually use dynamics to understand the size of these sets. And okay, you might ask, and it's not going to be too easy, and you might ask, why do you want to do that? Well, because in higher dimension, for example, if you try to approximate vectors, then it's going to be much easier to use dynamics rather than continued fractions, because in higher dimension you have no continued fractions. Okay, so this is why I want to switch to something more dynamical now. Okay, good, so let me erase this. Yeah, I don't remember. Okay, good. All right, so and to do dynamics, I need to introduce a new space. Okay, so this new space will be essentially a quotient of the tangent bundle of the hyperbolic plane, okay? But I want to take it slowly, and so I want to give you, at least introduce the notation, okay? So for me, the hyperbolic plane will be, I'll just take the upper half plane model, so x plus iy, such that y is strictly positive. And, okay, I want to endow, so h with hyperbolic metric, so Riemannian metrics, so which is 1 over y squared dx tensor dx plus dy tensor dy. Okay, so this means that the tangent plane, the tangent bundle of this space has just the shape ZV, such that Z lies in H, and V, I can just see it as a vector in C. Okay, so it just lies on the plane. And so the length of V at the point Z will just be given by the modulus of V divided by the imaginary part of V. Okay? Good. So, let's see. Thanks to this definition. Okay, so this, as we saw in
Imaginary part of Z.
of Z, sorry. Yes. Right, so as we saw yesterday in one of the lectures, this allows me to define a distance, okay? So this gives me a distance dh on h, which is defined in the following way. So first of all, for curves, for smooth piecewise smooth curves, gamma in h, I can define the length of gamma as the integral. So suppose that gamma goes from AV to h, then I can just set the length of gamma to be the integral from a to b of the derivative of gamma at the point gamma of t in dt. Right, so, and then this allows me to define the hyperbolic distance between x and y as the infimum of the length of gamma, such that gamma connects x to y. Okay, and I'm not going to prove this, but one can make the following remark. So the infimum is actually a minimum. A minimum, and is realized by curves that we call geodesics. Okay, so and these curves have the following shape. So here is my upper half plane. They are either half lines orthogonal to the line R. Okay, so this is my y larger than 0, or they are half circles whose center lies on the line R. Okay, so but this is for now we're not interested in this. Okay, so all right, and the fact that I have a Riemannian metric allows me also to define the unit tangent bundle of H. So I can define T1H to be the set of pairs ZV such that the length of V at the point Z is equal to 1. Okay, remember, this is the modulus of V divided by the imaginary part of Z. So what you will see is just so in order for this to have length 1, right, you have to take smaller and smaller circles as you approach here, okay, circles of radius y. Okay, so here you see big circles, and as you approach the line you see smaller and smaller circles, okay, and they all have radius 1 in this metric, okay, good. Okay, so now since I want to do dynamics, I need an action. Okay, so I consider, so I know, let's say I know that the group SL2R, okay, which is just the group of matrices A, B, C, D, such that the determinant is equal to 1, so AD minus BC, AD minus CB is equal to 1, acts on H. Okay, in the following way. So if I take G in SL2R, I can justify G acting on Z as AZ plus B divided by Cz plus D. Okay, so as an exercise, prove that for all G in SL2R, you have that GH is equal to H, and that this is an action. Okay, so that you can compose elements on this side. Okay? Okay, this is very easy. Alright, but okay, so if you look at the shape of this transformation, you see that this is a holomorphic map on the upper half plane, right? Since it is a holomorphic map, it means that it's allowed to have a differential, okay? And since it has a differential, I will also have an analogous action on the tangent bundle, okay? Or on, at least for now, on the tangent bundle. Then I will show that this action boils down to an action on the unit tangent bundle. Okay? So let's see. I forgot to say something important first. So, yeah, so if you have questions, feel free to ask. Okay? So, proposition. So, G preserves the length of vectors. In the sense that the length of the differential of G at Z applied to V at the point G Z is equal to the length of the original vector. Okay? And this is quite easy to show, so I'm just going to sketch the proof. So one has that the differential of G at Z is evaluated at a vector V. This is just an extremely easy computation. It's just given by 1 over Cz plus D squared times V. Okay? And one can also compute that, it's just a computation, the imaginary part of Gz is given by the imaginary part of Z divided by the modulus of Cz plus D squared. Okay, so knowing these two things, you can immediately compute, you immediately see that you have this equality, because the norm of dgz v at g point z is given by, so v divided by cz plus d squared divided by this. So the imaginary part of z divided by cz plus d squared. Okay, so this is nice and easy. Good. So, conclusion. Let me just erase this. So conclusion, so the action of G equals SL2R boils down, so induces, let's say, induces an action on the hyperbolic unit tangent bundle, okay? In the following sense, so one has the G time acting on Z V is equal to G acting on Z, and then the differential acting on V. Okay, and since we know that this preserves lengths, this is well defined because it sends vectors of length 1 to vectors of length 1. Okay, and also I make the following remark. So, yes, so plus and minus G act in the same way. Okay, so this follows immediately by the fact that the differential is given by this squared. Okay, so if you put a plus or minus, this really doesn't change. Okay, and clearly if you have a fraction az plus b divided by cz plus d, you can also change the sign of all your numbers and they give you the same thing. Okay, so effectively I can reduce this, I can see this as an action of SL2R modulus plus or minus the identity, which is usually known as PSL2R. Okay? Good. And there's an interesting thing about this action, that this action is simply transitive. So, proposition, the action of PSL2R is simply transitive. Of PSL2R on T1H. Okay, and why is this? Well, if you want to, so suppose you want to get the point x, again, let me give you a sketch of proof. Suppose that you want to obtain the point x plus iy, starting from any point, yeah, maybe I should define what's simple. Okay, transitive, you know what it means, and simply transitive, it means that you can do it in only one way. You can reach any element, but in only one way. Okay, so suppose you want to reach the point x plus iy, then starting from the point I, say, what you can do is you can apply the matrix 1x1 square root of y minus square root of y to the point I, and you will see that this goes to x plus iy. Okay? And then you can also see the following thing. So the stabilizer in G, or in PSL2Z, of the point I, so this is, I leave it as an exercise, is just PSO2R. So,
R instead of Z, we have subscript with tab.
excuse me, sorry? What? Yes, yes. Yes, exactly. Right, so the stabilizer of the action of this group on the hyperbolic plane is rotations, okay? And, sorry, the stabilizer of the element I under the action of this group is the group of rotations, okay? So, and then this means that you can use, you can use rotation matrices to send, say, the point II to any element ZV in T1H. Okay, so first you use the action by this matrix here, okay, so you send I to whatever element you want, and then you also compose by a rotation. Okay, and composing by a rotation allows you to send any tangent vector that you initially started with, for example, I, so the unit tangent vector pointing in the upwards, you can send it to any other point in the unit tangent vector. Okay, simply by rotating. Okay, good. So, and this proposition gives us, well, the opportunity to so introduce an identification between the group. So since the action of PSL2R on the unit tangent bundle is simply transitive, this gives us the opportunity to introduce an identification between the group PSL2R and the unit tangent bundle. Okay, so consequence, we have the identification so PSL2R T1H given by G is uniquely identified with the action of G on the element II. Okay, so this is just the point here with an arrow pointing upwards. Okay? By using G, you can send it wherever you want. Okay, so suppose you want to send it here, you find some G that sends this point here. Good. Okay, so the next step in this sort of process to define the space where the dynamics take place is to understand what the geodesics do. Okay, so in particular, let's see. So on the unit tangent bundle, so on E1H, I have the geodesic flow GT, which is just defined, as follow the geodesic exiting ZV. So remember, we we said that these curves that realize the length, so the distance between 2 points, are unique. So suppose that you have 2 points here, you have a unique geodesic connecting them, okay, and it will have some. So this is your geodesic gamma. It will have some tangent vector v at the point z. Okay, so you can act on this point zv by saying, okay, I have a time t. I follow the geodesic exactly by this time. Okay, and so what I want to do is I want to understand how this this flow looks like in the space PSL2R. So how does this look in PSL2R through the identification that I have here? Okay, so and to do this I have to be a little bit more precise. So I have to say what is the way to construct this unique geodesic. Okay, so I still have a little bit of time. So to do this, I have to identify how geodesics look like. Okay, and this is sort of, okay, it's not very difficult. So first we're going to do it in a very simple case. So suppose that this is the point I, and you have another point here, yi, with y being some positive real number, okay, bigger than 1, so y in r. I want to know how the geodesic connecting I and yi looks like. Okay, so definitely there is one curve that connects I and yi, and this curve is given by gamma t e to the power t I. Okay, and the length of this curve is what? Is the integral between 0 and log y of e to the t divided by e to the t and dt, which is just log y, okay? So this curve here looks like, here I have my point iy, here I have the point I, it looks like this. So I want to show that this curve is the curve that actually minimizes the length. And how do I do this? Well, suppose that you have another curve, so take eta another curve, then what you have is that the length of eta is equal to the integral, say, suppose that eta goes from ab to h, it's the integral from a to b of the modulus of eta dot t divided by the imaginary part of eta at t, and this is always bigger than what? The integral from a to b of the imaginary part of eta of t dot divided by the imaginary part of eta of t. Okay, and so this gives me precisely, so the integral is the logarithm of the imaginary part of eta of b minus the log of the imaginary part of eta of a. And this is just log y. Okay, so I have that this curve realizes the shortest length, because whenever I take another curve by this computation, the length of this curve is larger than log y. Okay? So I have uniquely identified the geodesic, I have identified one curve realizing the minimum between these 2 points. So how do the other curves look like? So suppose now I have some point z here, and so z1 and some z2. How do I connect z1 and z2? Good. So, and the fact is that by using the action of g that I have defined, I can always take z1 and z2 and pull them back to lie on the imaginary axis. Okay, so I'm not going to prove this, but I'll just write it down. So proposition, so for all z0, z1 in the unit tangent bundle, there is some g in SL2R or PSL2R such that g z0 is equal to I and g z1 is equal to IY, or YI. Okay, so knowing this, this one is clear because we know that the action is transitive. Okay, so I can always take a g that sends z0 to I. This is obvious. This one is less obvious, but you just do it by using rotations. Okay? So, okay, I'm not going to prove this. Good, so now knowing this, we have, say, z0, z1, this is I, and this is IY, so we have g sending, or maybe let's call it g to the -1 to make things more nice, okay? And here I have my curve gamma of t equal e to the ti. Okay, so in the unit tangent bundle, this curve looks like e to the ti, e to the ti, right? Because this is just gamma dot, right? So since this curve is unique, okay, and I know that G preserves distances, to understand how the geodesic connecting Z0 and Z1 looks like, I just need to apply G to this curve. Okay, so this means that the geodesic connecting, so since G is isometry, okay, the geodesic connecting Z0 to Z1 is just G acting on e to the ti, e to the ti. Okay? And the nice thing about this is that I can also see this. This is equal to what? G e to the t halves, e to the minus t halves, acting on I. Okay, so this is very easy to see. Okay, so so you have your G that is the point, right? And so e to the minus t halves, sorry, plus t halves, minus t halves, I is just equal to G acting on e to the t halves, I plus 0 divided by e to the minus t halves, I plus 0. Okay, and so this is just G e to the ti, okay, and analogously for the differential, okay, so dg sorry, what's the action on this part here, right? So you have G acting on sorry, let's put it this way, G e to the t halves, e to the minus t halves, here I only did this component, right? But on I will be this thing here, right? And on the second component, what do I have? I have G, so the action of dg at something, okay? And then I have 1 over e to the power minus t halves squared, okay? Fine. So this is just G acting on e to the t I. Okay, so if you don't see this immediately, you can do this by exercise. But remember, the differential of so this acts by differential, and the differential is 1 over c z plus d squared. Okay? So this is 1 over, where z is I, c is 0, and d is e to the minus t halves. Okay? Good. Perfect. So now I have a very cute thing going on. So you immediately see that the geodesics on the geodesic on the unit tangent bundle corresponds to multiplication by matrices of this shape. Okay? So consequence through the identification PSL2R T1H G identified with G acting on I have GT. So this GT is not an element of PSL2R. This is just the geodesic flow. Okay, so GT, sorry, excuse me. So GT ZV is just GT some G associated to ZV II, which is just G e to the minus t halves e to the t halves, or sorry, plus and minus here, I. Okay, so this means that GT G is equal to G multiplied by e to the t halves, e to the minus t halves. Okay, so good. This means that we have a geodesic flow, so we have a geodesic flow GT on T1H equals PSL2R. Okay? So you can also show that this is actually, this identification is also actually a diffeomorphism. Okay, it's a diffeomorphism, but to do this you need to identify what's the structure of PSL2R as a manifold. Okay, so, and this has the same structure of SL2R. Okay, because locally it's the open sets of SL2R modulo plus minus entity are the same as the open sets of SL2R. Okay, so the structure of this group here, and okay, so what's the structure on SL2R? SL2R is just a something in R to the 4. Right? So it's just a set in R to the 4, and so it has an induced, and it's also an open set. Sorry, not an open, what did I say? It's not an open set, but it's a manifold. Okay, because it's just defined by determinant being different from 0. So it's clearly a manifold, and you can push this structure of manifold on PSL2RZ. And through this, you can see that you can prove as an exercise that this is a diffeomorphism. Okay, so we have a very nice identification between the unit tangent bundle and this group, and we have a geodesic flow on the unit tangent bundle, which is, I give you a point and a direction, follow the direction, and a flow on this group here, multiplication by a matrix. Okay, good. So, yeah, I hope this was not too elementary for you. So what I'm going to do next time is the following thing. So we have this. So the fact that we have a flow on this space means that we can do dynamics. But the dynamics on this space is not interesting somehow. You know exactly what happens, right? So next time, in line with what other people showed. So next time I will fold PSL2R. Okay, so somehow, so this is just the unit tangent bundle. I will take a quotient of this unit tangent bundle and consider the same dynamics that I have on the unit tangent bundle, but in the quotient. And now it really becomes interesting. And analyzing the properties of this dynamics allows us to retrieve some information about Diophantine approximation. For now it's mysterious, but next time you will get a full statement saying if something happens in this folded space, if and only if some points have some Diophantine properties. Okay, so this is the gist of what will happen next time. Okay, so I think I can finish here.
Are there any questions? Let's thank the speaker again.
Okay.
And we'll meet back at 2:30 for the second session.
For your
Sorry? Ah, thank you, thanks. Yeah, maybe it was a bit too elegant.
Recording stopped.